Okay, so let's get going talking about how we can enhance and filter our attribute data to get better results. So here we've got kind of a fun demonstration that uses different filtering approaches. And we're using Kurt Marfer as our subject matter. So the image here shows us how varying processing techniques can affect our data clarity. So up on that top row, we're comparing the orientation adaptive filtering, orientation isotropy adaptive filtering, and Gaussian filters, at a smaller scale. And then down at the lower row, we see those same filters applied at a larger scale. And so you can kind of see how each method handles the edges and the details differently. And I like this visual because it really helps us understand why choosing the right filtering approach can be really important when we're doing our seismic data attribute analysis. Okay, so now let's look at a vertical slice through coherence data. And so what you're seeing here is the energy ratio similarity, multispectral display, and you can notice that there's some vertical smearing patterns that can make the interpretation challenging. And so this is why we need to use effective filtering techniques. Just note here that for coherence, we're going from 0.7 up to 1 coherence, which gives us a really good dynamic range to see some of these features. And so now we've applied the structure-oriented median filtering, and we can see how the image changes. So the filter has preserved the major structural features while reducing the noise. And you can also see how the vertical striping has been subdued a little bit, but still while maintaining those geologic features. And that's kind of exactly what we want, is reducing the noise without losing valuable information. And so this is an example of showing the coherence with the structure-oriented median trend removed from the data. And so this is quite different. So we can see how the discontinuities are much clearer. And this particular method is pretty useful when we want to emphasize the more subtle features that might be masked by those larger structural trends that we saw in the last image. And so these vertical lineaments are now more pronounced, which can be really helpful for fault interpretation. Also could be a good input for machine learning. Okay, now let's look at a time slice through coherence so that we can really see some of these differences. So this image shows us how coherence highlights discontinuities in the data. And you can see the fault patterns, particularly kind of on this right portion of the image. And so after we apply our structurally oriented filter to the time slice, you can notice how the noise has been reduced, but it still preserves a lot of those key faults. Let's see. We've gotten rid of a lot of the random noise here. And so let me just go back and forth a time or two. Let's see. So coherence without the filtering, with the filtering. And so it's really subtle. Pay attention kind of like right in this area that I'm pointing out, and then over here on the left-hand side too. And you'll just notice a lot of the reduction of that random noise. So without filtering, with filtering. Okay. And then here it is with the overall structurally oriented median trend removed. And so this would be that result. And so now you can see the edges of the filter. It's much clearer. And you could really get a good idea of some of these more complicated fault networks. And again, very, very good input for machine learning. Okay, so in previous lectures, I've mentioned the Kuwahara filter, and so I just want to bring it up again because it's been really great, and we found it very useful in terms of as a filter for seismic attribute data. And so it's a median filter that allows us to look at the overlapping windows and choose the right windows for filtering without kind of smearing across geologic features. And so what I'm going to show you is a different visual than I've shown before, trying to explain how it works. So here we've got a 2D Kuwahara filter system. And so we've got a grid right here where the gray scales hold on, let me just back up. So what we have is a 5x5 grid here. So we've got a 25 sample analysis window that's kind of centered on this red square right in the middle. The gray squares are showing us the 9 sample analysis window that we're going to move through. And the filter is looking at these gray windows and calculates their coefficient of variation. And so what it then does is it moves through, and I've got a little thing here. So it moves through those 9, keeping that red middle square selected because that's the one we're currently filtering for. But so we move through these, calculate the variation, because we want to make sure that the variation is not too high so we're not smearing potentially across geologic features. And then from this, we'll see which of these windows has the least coefficient of variation, and then that'll be the window that we smear over. So we're kind of doing a selection process to make sure we're not smearing out that geologic information. And then if we're doing this in 3 dimensions, we're also shifting it vertically, but this is just an example in 2 dimensions. So we can look at this image. We kind of find using people is a good way to show how filters work because we're so used to looking at people in real life. So this is a picture of GPHY from his paper that he published about Kuwahara filters when we first started incorporating it into the ASPE analyses, attribute analyses. And so what we're going to do is apply a Kuwahara filter, and you can see what it does to him, like to his face. It kind of preserves the edges, but it smooths kind of like the noisier areas, but it's getting the big picture about what's going on. We can also add some noise, so like some salt and pepper noise, random noise to his image, which is more kind of what we see in seismic data is having that noise. And so when we do the Kuwahara filtering, it's smoothing out the main features, also getting rid of that salt and pepper noise, which can really affect our seismic attribute analyses. So we're applying it to seismic data now instead of an image of a face. So this example shows 3 different versions of the same section. So we've got the original section up here of the seismic data. And then we've got a 3x3 median filter and then a 3x3 Kuwahara filter. And so you can kind of look through these and we've marked out some of the main features like the channel, the turbidite. We've got a large salt complex, a mass transport complex, and then a fault. And what you'll notice is that the median filter smooths out everything, including our feature edges. But the Kuwahara filter does a little bit better job of maintaining sharp boundaries and then smoothing within the facies. But you'll notice that like the median filter, it does tend to eliminate some of those thin anomalies like the fault, and then also the edges of the channel, which are up here. And so you want to be really careful about when you're filtering that you're choosing filtering that is appropriate for the geologic features that you're trying to observe. Okay, so we can also look at different seismic attributes before applying the Kuwahara filter. And so I've got 9 different ones here from one of our students' papers. And so we've got coherence, total energy, some GLCM attributes, reflector convergence, spectral bandwidth, all of them. And we've got them all in different color scales that have been optimized for each attribute so that we can get that information into our eyes and interpreted so we can see the patterns. So the attributes before Kuwahara filtering and then after. Okay, and so again, you can notice how the filter has enhanced some of the continuity of features, preserving the important boundaries, the features that mean something to us geologically. You can see the coherence here kind of maintains the major contrast, but it has a lot less reduced noise, or it has reduced the noise. The GLCM attributes over here have kind of a improved definition of the seismic facies boundaries without losing too much information. And so I'm just going to go back and forth a couple times just so you can see the difference. between them. So in terms of, having salt, we've got conformable sediments, we've got some mass transport deposits, kind of up in here. Well, they're easier to point out here. Mass transport deposits, conformable sediments, salt were the main features that we were looking at in this analysis. And so just going back and forth, you can kind of see the difference about how that Kuwahara filter gets rid of the noise and then and while maintaining a lot of the geology. Okay, so just to wrap up with image enhancement with filters, because we've found this a very, very important step when analyzing seismic data with attributes. We want to keep in mind that our attributes can be smoothed or sharpened along structural dip with different types of filters. We can do a couple of different methods that I've shown you here, and we have a lot more that we can use, a lot of different types of filters, and there's a lot of different filtering strategies. But some of the ones I showed you were how to subtract the median coherence along the structural dip, and that helps reduce stratigraphic anomalies while preserving the steeply dipping fault anomalies. So it's a good kind of preconditioning step for fault enhancement. And then the Kuwahara window uses, is one of our favorites right now. It uses a adaptive filtering technique to choose the window with the least amount of variance so that you're not smoothing across geologic features. And so it's been very, very useful to apply when we're doing machine learning algorithms. Thanks for listening.